In statistics, normal tests are used to determine if a data set conforms to a normal distribution with respect to shape, symmetry, percent of population within standard deviations, and the amount of tail. Tests imply that a sufficient sampling of the population will reveal if a normal distribution exists. In this video, we will explore how to determine if a sampling of a population is normal using Excel. When populations are normal, there are some powerful statistical tools such as the student's t-test and the analysis of variance that can be used to determine if the two groups are significantly different. For example, clinical drug trials that have an experimental group and a control group, or in geology, you might want to decide whether to split or lump two oil reservoirs based on porosity. There are several methods for evaluating normality. Common types include visual inspection of histograms or PDFs, comparing the mean, the median, and the mode, quantile plots, or normality tests such as the chi-squared test. Let's take a look at this example distribution. It's a normal distribution. It's made by random sampling 10,000 points from a population. It has symmetrical shape and the bell-shaped as well. If we look at the mean and the mode, they're both 50, as well as the median, or the P50. Skewness and kurtosis are also close to 0. So this would be a classical expression of a normal distribution. When we look at the quantile plot, we look at the theoretical z-scores versus the actual z-scores, and we see that it forms a straight line. This is also a signature of a normal distribution. In addition to the methods we just looked at, the visual inspection, the comparing of the central tendency and the quantile plot, there are 6 or 7 advanced normality tests that can also be used, but they're difficult to implement in Excel because they have long formulas that need to be written out, or optionally you can use Excel plugins which are much easier. One of the easier tools to implement is the Harkey-Barra test, which looks at both skewness and kurtosis. I've shown an example here and the formulas that you can use in Excel. Also, Excel has a built-in chi-squared function, but it's a bit of work to evaluate. It requires that the data need to be binned. The normality test functions are commonly available online or in other programming applications like R and Python. I recommend using these tools. In the event you want to compare two distributions but they're not normal, you can use the Box-Cox Transformation to convert these skewed distributions to normal. The Box-Cox uses a single exponent, lambda, to produce the normal distribution. Here is the formula that you can implement in Excel. To solve for the lambda, you can use Excel's what-if goal-seek function under the Data tab to solve for lambda, where the correlation for the QQ plot is set to 1, as we can see here. Here's an example of before and after the Box-Cox transformation, and the QQ plot shows that it's a straight line so that it's normal. We can also compare the before and after statistics, where we can look at how the mean and the median are different, and the skewness and kurtosis for the before data, and afterwards we see that the mean and the median are the same, and the skewness and kurtosis are basically 0. So at this point, let's move on to the Excel demonstration of normality test. In this workbook, we'll mainly look at the chi-squared test and examine it for different amounts of sample. For example, we'll do 5 samples, 50, and 100. We'll look at what it does with the triangle and beta distributions. We'll also look at a Kolmogorov-Smirnov test and some Python experiments that were done. And at the end, we'll explore doing a Box-Cox transformation. In this example, we'll examine a store manager's claim that he has the same number of customers each day. So, our null hypothesis is the same number of customers each day. To test his claim, we observed how many customers he had during the week. So it ranged from 40 to 53 customers a day. And the mean, which is the expected, is 50. Then we're going to apply a chi-square test, which is the chi-squared is equal to the sum of the observed minus the expected squared divided by the expected, which we've done here. And we sum that up and we get the chi-squared statistic. The degrees of freedom is the count minus 1, so we had 5 days, minus 1 is 4. And we're going to use a typical critical value of 5%. When we run it, we get a p-value of 0.359, or that is to say that there's a 35.9% chance that the null hypothesis is true. Over here we're going to do a dynamic test. We're going to change the parameters of the experiment so that on Fridays we'll allow the customers to be somewhere between 65 to 70, because most people get their paycheck on Friday and want to spend it. So what we do is we just hit F9 to recalculate, and we'll watch the box here where it says true. Oh, we got 70, it's false. 67, it's true. 69, it's false. 65, it's true. So we can allow for some dynamics and variability in the observations for these kinds of experiments. For example, with 50 samples ranging from 60 to 140. One population is uniform and the other population is normal. We can look at the statistics from our 50 samples. For the uniform, we can see that the mean and the median are very similar, so it's symmetrical. It's got a fairly broad standard deviation and no skewedness per se, and some kurtosis. And for the normal distribution, again, the mean and the median are about the same. The standard deviation is smaller, and there's very little skewness or kurtosis. In the inputs, I give it the min, the max, the mean, and the count, and the standard deviation is calculated by using the range rule, which I reference below, by Ramirez and Cox. The uniform distribution is made using these random values, just using the rand function, and with this little trick here where you look at the max minus the min times the rand plus the min, you can get a uniform distribution that conforms to the range that was set here between 60 and 140. And for the normal distribution, I just use the normal.m function, which requires the rand, the mean, and the standard deviation. For large data sets, such as this one here, the chi-squared requires binning roughly when you have samples more than about 15. The number of bins have a significant effect on the outcome of the analysis. Sturgis in 1926 indicated that a good rule of thumb for the number of bins is to use 1 plus the log 2 of the number of samples. Some authors suggest using between 6 to 10 bins simply. What I found from this example here is that when you have only 50 samples, it produces inconsistent outcomes for the uniform. Sometimes you'll get a normal looking outcome, in other words. But the same protocol with 1,000 samples that we'll look at next gives a pretty consistent outcome. With just 50 samples, we find that sometimes the histogram looks quite normal. The binning process requires us to use the chi-squared formula, which is the sum of the observed minus the expected squared divided by the expected. And we've applied it here to this bin data set. So I've used Sturgis's calculation to determine the number of bins, and I've calculated a bin size based on the range of the data. So here are my 6 bins where I've just added the the bin size to the min and just concurrently keep adding the bin size. And then I just use a frequency function in Excel to calculate the frequency, and I've used this conditional formatting tool up here to make the histogram. Here we've calculated a cumulative distribution function for the data, and here we've broken that down into their individual components, and they sum up to approximately 1, or basically they're the same as the continuous. And then the expected is the bin density times the count, where the count here is 50. And then we calculate the chi-squared value using the chi-squared formula. And we sum it. And this is your chi-squared statistic. So we've just passed it down here to this little table here. The degrees of freedom for this is the number of bins minus 1 minus another 2 for the mean and the standard deviation. We'll use the critical alpha value, or the critical value of 0.05. Then we calculate the p-value using the chi-square distribution, right-tailed formula from Excel. And here we've got a result of normal. So by pressing F9 in this workbook, I can rerun this simulation. And you can see, because we're using random numbers, we always get different p-values and chi-squared statistics, but almost always get a normal. Here's a case here where we got a non-normal, and you can see by just looking at this distribution here, this histogram, you can see that it's not really normal looking. Oh, we got another one. So it's not always consistent. You'll get sometimes you'll get a sampling that's not normal, even though you're sampling out of a normal distribution. If we come over here and look at the uniform distribution, we almost always get a non-normal. But again, because sometimes you'll get a distribution that looks normal. And see, we got one here. I've taken a couple of examples and made the QQ plot using this online calculator. And you can see it plots pretty much as a straight line. But on this one you can see these tails really zoom out. To demonstrate that you have to use the binning, I've done a unbin chi-square, which is hiding behind this text box here, but you can see the values going down. And I've summed them, and you get a statistic of 92. And even though it's normal, you'll see that we get a p-value that's very, very small. It's like e to the minus 9. So I'll just run that a few times, and you can see you're going to pretty consistently get a non-normal result. So this shows what we get when we run 50 samples. Now let's move on to 1,000 samples. This worksheet is the same as the previous worksheet, except now our example has 1,000 samples. And we'll find that we get more consistent results with respect to p-values greater than 0.5 or p-values less than 0.05, which produce a normal and non-normal result respectively. So let's hit F9 and let's watch what happens with the p-values and the results. So let's continue with these simulations. Also, look at the histograms that are being produced above. You can see that they're more consistent as well, looking normal over here and uniform over here. Also, when we look at the QQ plots, we can see that for the normal distribution we get a very nice straight line, and we get these excursions away from the straight line on the uniform. So next we're going to look at the normality test we get from symmetrical triangle and beta distributions. In this example, I'd like to examine a beta and triangle distribution and see how they compare to a normal distribution. In this example, we see that the beta in black and the triangle in red how it compares to the normal in blue. And we can see that the triangle and the beta are both bounded, so they don't continue out, whereas the normal, its tails continue out. The nice thing about the beta distribution is that its dispersion can be modified with a dispersion function called lambda. And for example, here it's 12, but let's make this 0.001, and let's see what happens to the black curve. And I'll hit F9, and it becomes a uniform distribution. With 4, a value of 4, it becomes more of a dome-shaped feature. And with a value of around 10, it approximates a normal distribution. Now we'll scroll over to the right side of the workbook and take a look at the normality tests. In this section of the worksheet is where we do the calculations for the distributions and the z-scores and the QQ plotting. Over on the left, we calculate the random values between 0 and 1. We calculate the normal distribution, the beta distribution, and the triangle distribution, which is quite a long formula. And then we calculate the z-score of one of the selected distributions, which we designate over here with this drop-down menu. And then this part here is where we do the calculations for the QQ plot, which are just a series of sequential numbers. We calculate the probability, which is I minus 0.5 divided by the count. And then we do the z-score of the standard normal distribution. And here we're just taking the z-score values that we calculated over here, and we're sorting them. Now let's scroll over to the right and examine this other part of the worksheet. That's good. And we can see here we have our distributions, as we saw before, and where we can adjust the lambda. Over here is where we can pick out which distribution we want to do the QQ plot for. So right now it's on the triangle, and I can change that to the normal and hit F9, and you can see it changes, and do the same thing with the beta. Alright, then down below we have the descriptive statistics for the different distributions, and where we calculate the RK-Bera normality test for each of the distributions in question. And over here we do the chi-square testing. These calculations are done down here. This is the binning for the chi-square distributions, and you can see that we're doing 620 counts for the normal, the beta, the triangle, and we're doing 5,000 calculations for the standard normal distribution. So let's run a series of simulations to see how the normality tests work. I've set the QQ plot to normal, and if we look at it now, we can see there's a point out here, large blue point that's falling off the line, which might have repercussions. And you can see that the standard normal is coming out not normal. But let's run some simulations and see what happens. First, let's look at the RK-Bera test results. So here we go. I'm just hitting F9 over and over and see if we come up with a not normal. And it's looking pretty good. You can see that up above the QQ plot keeps changing a bit. So for the most part, it looks like the RK-Bera is not sensitive to that the RK-Bera is not really sensitive to the normality. Let's take a look here, down here at the chi-squared, and it says here that the triangle is not normal. Let's go below and take a look here at the triangle, and it looks fairly normal, but let's change this to triangle and look at the QQ plot. F9, and you can see here how it's falling off the line. So let's just run a series of these to see what happens. Beta is not normal. Let's take a look at the beta. And we can see that there's a few points falling off the line. So let's just keep running this. And what we're finding is that sometimes the triangle comes out normal. And remember, this is for 620 samples, except for the standard normal. And it leads me to believe that the number of samples that you run may have an effect on the outcome of these normality tests. To see if the number of samples have an effect on the normality test, I did a Python experiment, and I have the results down below here. And what I did was I ran 500 trials, and I ran it 5 times, and I did it changing the number of samples. And here I'm just putting it the mean. And so you find that so this is for a beta distribution. And we see that if I run 20 samples, 426 times out of 500 trials, I'll get a p-value greater than 0.05. At 50 samples, similar results. At 100 samples, similar results. But when I get to 500, it starts to recognize that the tails are not quite right. And you get a fewer successful counts of these p-values greater than 0.05. At 1,000, you get a minuscule 43 out of 500. And by the time you do 10,000 samples, it really knows that it's not normal. In this worksheet, we'll look at the Kolmogorov-Smirnov normality test. This test is much easier to execute in Excel than the chi-squared test, and can be either done in an unbinned analysis or a binned analysis. We will compare the both of these techniques in this worksheet. The Kolmogorov-Smirnov test, or KS test for short, basically looks at the difference between the cumulative distribution function for a normal distribution and the cumulative density function for the distribution that you're evaluating. And the KS statistic is the maximum difference between these. In this workbook, we'll evaluate some beta distributions, which have the inputs of a most likely of 100, 75, and a max of 125. And we'll put in here a dispersion factor, or lambda, of 10, which is close to a normal distribution. It calculates the alpha and beta required for the analysis. So let's see how this workbook does its job. In column H, we calculate the beta distribution. And then in column A is basically just the sorted version of column H. In this example, we're going to calculate this for 1,000 samples. The rank is just the number of sequentials. And then the expected is basically the rank divided by the count. And the rank minus the count is divided by the count. And in column D, it's the rank minus 1 divided by the count. In column E, we calculate the standard normal distribution. In column F, we calculate the distribution for a normal distribution. And then the difference between the actual or standard that we've done and the standard normal is this difference. The KS statistic is the maximum value of this difference. In this analysis, we saw that the mean is 100, the median is 100, the standard deviation is about 7, and very small kurtosis and skewness. It's a very symmetrical, as we can see here in this distribution on the binned data. This is a binned data. The binned data is a technique that I found in the realstatistics.com workbooks. I have a reference down below that you can look at for finding this right here. But you can also do it unbinned. When we look at this, we see that the Ks statistic is smaller than the Ks table value. I have the Ks table values over here on the right, where you can look these up. And when we look at the difference between the two cumulative distribution functions of the observed and the expected, we see they basically overlay each other. And here in the black line, we look at the difference for these x values. The black is the unbinned analysis, and the brown is from the table. Both the unbinned and the bin say that this is probably normal. Now we can run this multiple times by hitting the F9 key, and pretty consistently this turns out to be probably normal. If we broaden the dispersion, we'll make the lambda 1, then we can see that we get some inconsistent results between the binned and the non-binned analysis. So they both say not normal, probably normal, probably not normal, probably not normal, probably not normal, probably not normal, probably normal. You can see that's practically a uniform distribution. If we make the lambda 0.001, then we're basically looking at a uniform distribution, and let's see what we get here. Both of them say probably not normal, probably not normal, probably not normal, probably not normal. Let's change the lambda back to 10, but in this case here, let's make this a skewed distribution. So we'll change the max to 200, and we'll see what we get on our results. So the unbinned says probably normal for both of these. Probably not normal, probably normal, probably not normal, probably normal. One more time. Probably normal, probably normal. So you can get some inconsistent results with this. Just for the fun of this, we're going to switch over to an online calculation of this data set and see what happens. And to do that, we'll just copy the sorted data, scroll down to the Kolmogorov-Smirnov and Lilliefors-Shapiro-Wilks calculator, and in this spreadsheet we'll just clear what's there, and we'll paste in our data that I copied just a few seconds ago. Okay, so here we want to do the Kolmogorov-Smirnov test. We're going to test it for a normal distribution with a significance level or an alpha of 0.05, and then we'll calculate. What I like about this is that you'll get a lot of nice graphics. It says it's asymmetrical, skewed shape, and it's potentially mesokurtic, or normal-like tails. Here we get a statistics of 0.42. The online calculator reports a p-value greater than 0.05, but just barely, which would indicate that is a normal distribution still, but we know it's asymmetrical. So let's change this, make it a little bit more skewed, and see what happens. Switching back to our spreadsheet, let's make this 300. F9. Probably not normal, probably not normal. Let's do this a few times, see what we get. It's consistently giving a probably not normal answer. Let's see what the online calculator does. So again, we'll copy the data, switch to the online calculator, we'll clear what we had in there before and paste in our new data, and we'll calculate. It says here this is smaller than 0.05. This is definitely not normal. What I like about this data set is it gives you the QQ. It gives you the cumulative distribution. You can see the histogram, and you can see the Dmax. So All in all, I think this online calculator is pretty slick. Let's compare so let's look at the test statistic, 0.07, and let's compare this to what we have in Excel. And 0.07, 0.066, so pretty close. In this workbook, we'll examine the effect of sample size on normality tests. Beta distributions with shape factors of alpha and beta equal to 3, or broadly symmetrical distributions, were made for a series of sample sizes ranging from 20 to 5,000. We can look at the histograms from 20, which doesn't look particularly symmetrical, and we see as we get to higher samples, they look increasingly more symmetrical and more like a normal distribution. Now let's look at the QQ plots associated with these histograms. We can see here at 20 we get a fairly linear looking trend, but a very limited range of z-values going from about -2 to 2. When we get to higher samples, we see that the range of z-values increase, and we start to see some of the samples deviating from the straight line. And as we go to 100 and by 500, we see strong deviation along the tails at these higher z-value ranges. By the time we get to 5,000 samples, we see strong deviation from the straight line and z-values going out to almost 4 standard deviations. A table was created to show the results of this analysis for different types of normality tests. And at the lower sampling levels, we see that they all show normal distributions. And as we get higher in the sample range, we start to see that some of these tests are more sensitive and produce not normal distributions. At 1,000, the chi-squared gives ambiguous results. Sometimes when you run the test, it's normal, and sometimes not normal. And by 5,000, all of them say not normal. I should warn you here that we probably shouldn't say normal and not normal, but we should say probably normal and probably not normal respectively, because due to the random sampling of the beta distributions, we sometimes can get different results. If you want to see more about this, I'll refer you to these links here for my GitHub site, and you can look at the Python codes, download them and run them. I'll also leave a link in the video description. When you want to compare two groups of data for a hypothesis test, such as the t-test or ANOVA, the data need to be in a normal distribution. But often we find that the data are not normal. In such cases, we can use what's called a Box-Cox Transformation to convert the data to normal. In this short video, I'll demonstrate how it works. It's basically accomplished with a power transform, and the formula is yi, which is your transform data, equals the original data raised to the exponent lambda minus 1 divided by lambda, and lambda cannot equal 0. As you can see in the two histograms, we had a before data, which is a log normal distribution, and we transformed it to a normal distribution. And to the right are the QQ plots that demonstrate normality, where it should be a straight line. Here's the before and here's the after. Let's take a look at the data to see how this works out. So I've put in a log normal distribution with 5,000 observations. Here's where we solved it. We set up a set of sequential numbers, 1 to 5,000, and we calculate the probability, which is basically the value I minus 0.5 divided by the count. And then we calculate the z-score, or it's basically a standard normal distribution, which is our theoretical distribution. Here we calculate the z-score for our transformed data, which is B5, or over here our transformed information, minus the transformed mean divided by the transformed standard deviation. And in this column here we just sort our z-scores, and over in these two columns I've done the z-scores for our raw data. Let's take a look at the statistics of our data before and after. So the thing to notice about here is that the mean and the median are significantly different, as you would expect with this log normal distribution, and the standard deviation is very high. The skewness and the kurtosis are also very strong. And after we transform it, we see that the mean and the median are pretty much the same. The skewness and the kurtosis are also quite small. So I think the big question is, how do you calculate lambda or solve for lambda in Excel? And what we did was, first off, we need to know what the correlation is between the z-score from our theoretical and the z-score from what we calculate from our transformed data. We want this to be 1. So we want a good correlation. And how we do that is we use, under the Data tab, Goal Seek, where we take where we set the correlation to what we want, have a value of 1, by changing the lambda value. Sometimes it takes a little while to calculate, but this does a pretty good job of solving for lambda. And that's basically how we do a Box-Cox transformation.